Hello everyone. In this tutorial we will understand another circuit of rectification circuits for producing high voltage DC, and this circuit is called full wave rectifier with center tapped high voltage transformer. So high voltage DC can be produced by using full wave rectifier with center tapped high voltage transformer. We use full wave rectifier instead of half wave rectifier, as full wave rectifier has big advantage than half wave rectifier, and this advantage is the ripple voltage is reduced in case of full wave rectifier compared to half wave rectifier. Thus, single phase full wave rectifier circuits can be used for high voltage applications only if the high voltage tension winding of the transformer, which is the secondary of the high voltage transformer, is earthed at its midpoint, and if the DC output is single-ended ground. So what is the meaning of that? This is the equivalent circuit of our full wave rectifier with center tapped high voltage transformer. This is the primary of our high voltage transformer, and this is the secondary. It can be observed and noticed that the midpoint of the secondary winding of the high voltage transformer should be grounded, as we saw, to use this method, full wave rectifier with center tapped high voltage transformer. So the midpoint of the secondary should be earthed like this. As a result, two voltages will be produced, V1 and V2. V1 here is half of the voltage of the secondary of the high voltage transformer, and also V2 is like V1. Also V1 is out of phase from V2. So this is our equivalent circuit. In this circuit we use two diodes. First diode D1 and the second diode is D2. D1 is connected in series with V1 and D2 is connected also in series with V2. Also we have the capacitor, of course, to reduce the ripple, and we have also RL, which represents our load. Here is the output voltage, and we can predict that this voltage is, of course, will be high voltage DC. Now let's see the operation of our circuit. So this is our circuit, and this is the waveforms of our voltage. First, we have the dotted sinusoidal waveform is V2, is the voltage V2, and the solid sinusoidal wave is V1. We can observe that V1 is out of phase from V2. The phase shift between V1 and V2 is 180 degrees. Also we have the output voltage here with the blue line. This is the output voltage, and of course it's a DC voltage with ripple. The ripple is called delta V, and the difference between the maximum and minimum is called 2 delta V, while delta V is the ripple voltage. Now let's see how we can deduce this output voltage. Let's see the operation of our circuit. First of all, in the positive half cycle, from this point to this point, the positive half cycle, during the positive half cycle, the diode D1 will conduct the voltage across D1 will be positive, so D1 acts as a short circuit, so the capacitor C charges in that direction. This is the direction of charging the capacitor while D1 is on. The capacitor C1 charges until the voltage across the capacitor equals V1 maximum, which is the maximum voltage of V1 at this point. At this point, D1 will be off, as the voltage across it will be negative, so it will be open circuit. At this moment, the capacitor C will discharge across the resistance at that direction. So D1 will off and the capacitor discharges through the load resistance RL. During the negative half cycle, from this point to this point, during the negative half cycle, the voltage across diode D2 will be positive, so diode D2 will be short circuit and the capacitor C will charge in that direction. Let's see the direction of charging the capacitor. When D2 is on, the capacitor charges through that direction, as we see. This is the direction of charging the capacitor. So the capacitor is charged until the voltage across the capacitor reaches the value V2 maximum. This is the value V2 maximum. As you see, this is a waveform of V2, and this is the maximum value of V2, which is V2 maximum. When the voltage across the capacitor reaches V2 maximum, the capacitor discharges through the resistance RL in that direction, and the diode D2 will be off. So the capacitor discharges through the resistance RL. Then the operation of the circuit will be repeated, and this is finally the output waveform of this circuit. Now let's see the important features of full wave rectifier using center tapped high voltage transformer circuit. The first, the ripple voltage in full wave rectifier is halved compared to half wave rectifier circuit. So this is an advantage for this full wave rectifier circuit, that the ripple voltage is decreased to half value compared to half wave rectifier circuit. So the ripple voltage will be V maximum over 4FRL times C. F is the supply frequency, and RL is the resistance of the test object, and C is the capacitance and or the smoothing capacitor, the value of the capacitance of or the value of the smoothing capacitor. But V maximum here, what is the value of V maximum, or what is V maximum? Here, V maximum, which is the maximum output DC voltage produced in this rectifier circuit, is approximately equal to half the peak value of the AC voltage of the secondary of high voltage transformer. Here, this is an important consideration only in this circuit, because in this circuit we use center tapped high voltage transformer. The secondary of high voltage transformer is earthed at the midpoint of the secondary of high voltage transformer. So V1 and V2 will be produced, and V1 or V2 is equal to half of the total secondary voltage of the high voltage transformer. So the maximum voltage here is half of the secondary voltage of high voltage transformer, and also the DC above voltage can be obtained from this formula. The DC voltage equals V maximum negative the ripple voltage, so it's equal V maximum times 1 negative 1 over 4FRL. See? So the ripple voltage here is decreased, which is an advantage, but the maximum voltage here is decreased to the half value of the maximum of the secondary, which is here is an disadvantage. So that's all about full wave rectifier circuit using high voltage center tap transformer. Thank you for your listening.